we'll go with it anyway.
Really?
No, because his RA was doing that. He was taking polls of what color should X subject output be. And it said that, not Andrew, but the RA actually told me that he was gonna like collect all the data, put it on the spreadsheet, and then share the spreadsheet.
The question is, what color should the spreadsheet be? Only answer is green because it's stuff.
White and black.
Stay away from them.
White and black is the most efficient for a paper print.
Don't disrespect you.
Yeah, and I don't have, there's no camera today for some reason. I don't know what's going on with it.
Is the screen share right?
Yeah, the screen share is worth, like we're up. We got sound, we're in, we're going. All right, so time to build up quiz number 2. And first question is always like, what was this about? Like why, what were the topics? What were the things that we were working on? And then next step is like, how do I demonstrate that I understand that material? So what's kind of a question or a problem engineering approach? So first, let's figure out like what topics and ideas, and then we'll get into like problems, questions. All right. I like note cards, so I'll hand out. Just because it's like less formal, you know? We're just trying to get some ideas. Yeah, you should go check it out. I need one before.
Oh, I got you. Here you go. Wait, how many degrees of freedom does that fly with? One. That's what we all call.
Yeah, nice. All right.
That is very
Doing something right.
relevant concept right there.
Maybe an X bar linkage.
What?
So like because we did 4 bars and we did.
Whoa, hey.
We did 2 bars once.
Adam,
What?
I'm gonna ask you to cool your jets. Okay? Because you know how many coolies
An infinite bar linkage.
Yeah.
Actually, you'd solve it the exact same way. You'd solve it the exact same way. You could just write a program to do it.
I don't want to do that for a quiz.
I'll do it. Collaborate on the GitHub that no one responds to.
Is it just us?
I have about half the posts on there.
Nice.
Yeah. No, Andrew responded to one of mine.
Nice.
And I made you guys respond to the other. So
Yeah, because on the homework we did a 2 bar linkage with like constraints.
that was 4 bar. What are you talking
No. The problem before.
Oh yeah, that's 2 bar linkage.
Yeah, like motionless constraints.
I don't understand what the 4th bar is in problem 3. There's 3 bars. Is there one invisible bar?
Yes.
Okay. I guess you could put a bar, just move it.
That one's called like a slider crank. Yeah,
The 4 bar linkage?
Yeah, that one.
That's what they call me in high school.
Like when you have one.
Calm down.
That's what they call me in high school.
True.
Do I bring my stuff with me to the career fair? I'm gonna change it.
You are overthinking this one.
I am over.
That one's called like, we were looking at like 2 bars moving, but it wasn't, with like a 4-bar linkage, we had 4 pins. In this case, we have like 3 pins and then 1 sliding constraint. So this one's called a slider crank. One piece slides and then the other crank is moving in a circle. So you turn rotational motion into reciprocal motion. Why would you ever want to do that? That sounds crazy. What is that used for?
Engine.
Engine, yeah.
Piston cylinder.
Yeah,
simply
piston,
servo.
yeah.
Yes.
So slider crank is like classic engine dynamics.
Sure. You're just good at that. No, I'm just a D1 hitter. You just got lucky. I don't get lucky.
Do the honors aside from that.
Yeah, 98% is not lucky. I don't blame you on that one. Guys, I'm thinking vectors.
Vectors, yeah. Taking up vectors again. The disc.
You mean the flywheel problem, Adam?
Yeah.
Yeah.
Well, it was like the flywheel, but we also went over another problem where it was like a record player with an and function on it.
Yeah, okay.
That's what I've asked about the equation.
Yeah, for.
Can I ask, what did we end up? I don't think we ended up using equation 8.21.
We didn't end up using it, so
I'm just curious what it's for.
yeah. Like you can use it, like all that 4-bar linkage math that we did, you could use it for that. Like we could have said, these are all rotating reference frames.
Okay.
Each bar is rotating at a theta 2 dot, theta 3 dot, theta 1 dot. And then we could have derived what the relative velocities were that way. I just find it easier to like plug in sines and cosines. Yeah, that might just be me though. Yeah, what was with the flywheel? What were we doing there? Angular momentum, yeah.
Pseudostatic problem. Or you said something along those lines. Not pseudostatic.
Oh, quasi-static, but that one was definitely like dynamic. Like it was moving, but there was something about it that was a little different.
I thought we valued it like kind of like it was static, so right?
In that one, I think that was that
So
like.
it's just, I guess it's just the idea that since it's not moving in the X direction, it's just rotating, that the forces must be equal.
Yeah. Oh yeah, yeah. So there was like, it wasn't gonna move left or right or up or down, but there was something about that. Like we knew how fast it accelerated, and we were trying to solve for forces. What is that called? This is a great, like, especially if you're going to career fair, the vocab that you use to describe these problems is like, that's the way to do it. So this one, like, if I know the motion, I can solve for the forces. The fancy way to say that is that your inverse dynamics problem. So you know that something is going to do something, so then you solve for the forces that you need to do that. So like inverse dynamics.
You don't have to give it back. You need it for today.
Oh, I got mine.
Okay. Did it bleed everywhere? Usually it does that.
No, I don't really. That's
Exploding.
Bless you. It's a little, like, at first it didn't write.
Yeah, it does that.
And then it
Alright, what about the
Inverse dynamics is huge, especially in like biomechanics applications, because a lot of times there's no way to actually measure like a force on a kneecap, but you can like kind of put sensors all over a person and measure kinematics, like what are the accelerations, you can even look at like strain and displacements and all sorts of stuff. So then you're doing an inverse kinematics problem of like, I know the body did this, and I know this is how it moved, so what were the forces in each of the muscles to create that motion? It's like good inverse dynamics problem solving. What else? Did I catch everything already?
we also had like the problem too. We had like prismatic type
Yeah, like different types of constraints. So like degrees of freedom. And constraints is like if we know a body has some way to describe where it is, and then there are constraints on its motion, the degrees of freedom reduces by the number of constraints, kind of that way. So there were prismatic constraints, there are hinge constraints. You could have just a fixed constraint that these two things have to move together, like if one rotates, the other one rotates. Yeah, all sorts of stuff. Usually in 2 dimensions, at least like planar motion, it's either prismatic, a hinge, fixed, and then like chords, like pulley systems would be the other. Sorry.
So on like the first quiz, I was supposed to make a kinetic diagram. How would that work for like these types of setups, like the 4-bar linkages?
If you were trying to look at like what is the kinetic diagram of a 4-bar linkage,
Yeah.
there, like each moving part would have a kinetic diagram. So let's, just because there's less moving parts, let's look at like just that first problem. At least like similar kind of problem, right? So like if this is the thing and I know this is moving at whatever, theta dot equals, go something fast, 100 radians per second. So this thing's like cranking away. We have internal combustion engine, it's moving. 100, maybe that would be, it's like probably diesel engine, hundreds of RPM. I guess still divide by 6 though. Anyway, so now I could break this up into like 1, 2, like, sorry, 1, 2, 3. Link 1, I could say some kind of torque. Here's like Ry, Rx. I don't know why I drew it that way. And in this case, what I'm going to do is like A around that O point, since it's rotating around there, I would have like the main motion is all going to be change in angular momentum around that point. So if it's moving at a constant rate, alpha is 0. So some of the moments has to be 0 somehow. And then number 2, give myself a little bit of room. Ugly. This one has the most complicated motion because it's moving and rotating. We'll be able to use constraints to figure out like how that moving and rotating is connected, but we have to consider all three components, like the fact that it's rotating around itself and there's an MAY and an MAX. And then the last one is the relatively easy one, because I can say there's a BX, a BY, some kind of like normal force down, and then some kind of like MAX. So I split it up, at least if we're trying to draw like what are the free body diagrams and kinetic diagrams for this system, every moving part is really considered another FBD kinetic diagram, so splitting it up that way. How's that? Seems okay. We didn't really jump into like how this is all how all these forces are connected, because a lot of time, in this case, like it's probably not too bad to go through and kind of solve for these. Like we did it once, and we could probably do it for the moving part, but usually once you get moving systems like this, you plug it into some kind of like multi-body dynamic solver, and then it would just like plop out all those reaction forces, all the constraint forces, all that stuff for you. Anyway, yeah, just an aside. What else came up as you were thinking about like what module 2 was about? I think I didn't like see everybody's note card, but did we miss anything? Good. All right. And how do we show that we know like some of this, or like some important ideas from these topics, like degrees of freedom and constraints, or slider cranks, 4-bar linkages? Like, what do we want to do here? Inverse dynamics, and like maybe we don't want to go through the full like inverse dynamics of a 4-bar linkage problem, unless a few of them are like, it's nice when you assume massless bars, because then some of the forces have to be 0, because if M is 0, MA has to be 0. That's why sometimes it's like, assume that this connecting link is 0 mass. Like, well, that's a weird assumption, but it helps because now some of the forces is 0, even though it is moving. Anyway, yeah. So what kind of problem or question? What are we thinking there? Yeah.
A good question might be some sort of linkage where we have to identify the degrees of freedom, like, and specifically which constraints cause it. So like, how many degrees of freedom are you losing due to hinges? How many are you losing due to like a prismatic interaction?
Okay.
And then just solving, given the rotation rate of one of them, and given the lengths and vectors, kind of like we did on the homework, just to solve for them.
That would make sense. Any specific, or did you have like?
Oh, I didn't.
Okay. Yeah. That's okay. Yeah, that would work. Were you thinking 4-bar? Oh yeah. You want to go through all that math again?
I mean, we already derived it.
We did a lot of the initial work. Oh man, how many degrees of freedom is that?
You also did the same.
More? Yeah. Yeah, is this one fixed?
Oh yeah, I think that was one.
You what?
I did that yesterday.
Did I send you what I got?
Okay.
You
So
sent me
is the
some
whole
of
system
Oh, yeah.
with the flywheel, or is it
You ever need stuff, just ask me.
Okay. And then bars, if the flywheel moves the whole system.
I was busy applying for the job.
Yeah.
Employment activity. I think we did the 4 bar linkage.
Yeah, I just capped on, like, capped on, yeah, it's like my initial phase.
4 bar linkage. Mechanics and materials? Like the most recent lecture video about the dissertation?
Yeah. Okay. How?
The negative sign. Some of the problems literally say put a negative sign. And then some of them have it built in. I'm like,
And that, I'm talking about like algebra.
Alright,
I guess like
have
what was the second? Oh, like doing it again.
oh yeah.
Yeah. Because second one of inertia, I hate it. I hate finding exponent and I power. Yeah.
And I realized that because I watched those examples as I accidentally left one with my number was
Yeah, that happens to me as well.
I was like, dude. I was like after like 5 times. And then my friend was like, you do realize that number is
Oh yeah.
yeah. And some friend is like, yeah, but only replace it.
When you do that, Scott, if you email her and copy the TAs,
No, I know.
one of them always responds within 2 hours. So really fast. She is awesome.
Have you come across this problem before where
It's a Gaussian surface.
a Gauss surface? No, not a Gauss surface.
A donut is rotating.
Rotating in which direction across which axis?
So like a spool of like thread or cord. Have you seen this before?
I mean, I've seen if you like pull it at a certain angle, it's going to go backwards. But when you reduce angle, it'll go forwards.
Yeah.
We should review that for those of us who may not know what Adam was talking about there.
I just saw it on like a random YouTube video, so that was fascinating. Like,
Yeah, so the idea is like,
I see, when you put the arrow, I know exactly what it sounds like how you do the yo-yo trick with walking the dogs.
yeah, so here if I like pull on a cord on a spool, so the bottom, this thing is not gonna slide, like it has to roll somehow, and I pull with tension that way, is it gonna go forward or is it gonna go backward? Backward?
Yeah.
Forward in this case.
No.
What?
If you change the angle.
Because the wheel is going to push
Alright, what's the
to
angle?
the left.
What's the angle right now?
Parallel with the floor. I'm just like pulling it. It's a weird question, right? Like it's similar to the flywheel, right? We're creating a torque and trying. Here, this isn't really like inverse dynamics problem. It's more of like a dynamics problem, but it is directly connected to like what is alpha. We know that this whole thing has I theta double dot. Like it's going to do something. Either it's going to increase that, like we're pulling on it this way, so it's going to roll towards us, or we're pulling on it that way and friction's going to push it the other way. Right? And what do we think? Do you want to like figure it out? or just leave it as a mystery?
We should talk. I low-key want to know. And I'm gonna do this when I go home.
But you don't want to do it? All
I
right.
can like theorize, but I don't know the math enough. How do we prove?
I mean, main
How do we
thing.
find that like critical angle when it'll like change? What?
Main thing is that it's the same process that we've been using, right? So I know there's a T this way and some kind of like force of friction that way. And yeah, we can say there's like a mg, but for the most part, n equals mg, like it's not jumping off the table. All that.
So the angle doesn't, in that case, the angle kind of depends on friction.
Yeah, but here friction is not mu times n, which that part is a little weird for most people. Like, because if something's just like sitting on a table, friction is not mu times the weight of the thing, because then as soon as you put something down, it can slide away. But friction is just there. It's big enough that it can't slide. That's the main like friction there. And then we have like MAX, and then I theta double dot. So now I know MAX equals T minus that force of friction. I don't know what force of friction is, but I do know that that has to be true. I theta double dot is, now I need to know like how big the spool is, right? Because it's different if T and F are directly in line with each other versus T right at the center and force of friction all the way at the bottom. So let's call this like 0.1 meters, and this one 0.2, like it's double the spread, something like that. So now T is positive. Something like this.
Is that just a moment equation?
Just moments, yeah. All
I theta double dot is moment?
this one is describing like change in angular momentum. So that's some kind of like mr squared over 2, or like something, like some factor of r squared times mr squared somehow. What do we do now though? We don't know T, we don't know theta dot, double dot, and we don't know F. Well, maybe we know T, we could say. Let's say we know T. We're pulling on it with 10 newtons force, right? What do we do now?
Now we can solve because we have two equations and two unknowns. Because MAX should be 0 because it's not moving in the x direction.
It's definitely going to move one way or the other.
It's going to move, but it's not going to accelerate.
It's going to accelerate. Yeah.
It's going to accelerate.
Yeah, if you
Well, we
have...
know the mass, though. We can just give it an arbitrary.
We can give it mass, yeah. What's the connection between acceleration and angle? Or distance and angle? What's the connection between distance and angle?
Pi r.
Yeah, so if you think about circumference of the circle, right? Every time you rotate 2 pi, you've moved 1 circumference. So every theta, every unit of theta, you're moving r theta. So really I could call this Or, well, what do I want to leave it as MAX to so then we can figure out is AX positive, negative? That would help.
Yeah.
So R theta double dot equals AX. Now we're making progress, right? Because now we have two equations, two unknowns to figure out. And let's say I like the MR squared over 2. Get rid of that one, get rid of that.
Where did you get that? Home or here?
That one is for a disk.
Okay.
Like if it's just.
So can you explain why you're able to add into R theta double dot?
If I say R theta equals like distance traveled and R, oh really? Yeah, now that I think about it, it should be a negative, right? Like if I increase the angle this way, I should move backwards. And if I decrease angle, then I should move forward. Kind of like that. So now I should be able to like solve for force of friction and then get rid of it, solve for AX. What do we think, positive or negative? What's it gonna be? Good so far?
Where is the negative?
The negative?
Is your negative MR?
A negative MR?
Focus on
Oh, and the left-hand side? Yeah, yeah, that one's still negative. Yeah.
That's supposed to be 10.
I did like 10 times 0.2, which was, did I call it 5? Did I call it 4? Or 2? Should be 2, right? 1 minus 2. Yeah.
Why did that 1 become, or why did that 10 become 1?
So I had 1 minus 0.2 times 10, so I just did 1 minus 2, which is a negative 1. Bring it over to the other side. I'm doing like some magic arrow math here of like just trying to get to punchline, but all algebra, and maybe I missed, but for the most part, the thing that we're figuring out is A is going to be a positive number. It's going to move forward because we're pulling on it forward. Yeah.
Which R would we use in our final equation? I don't know if it's final.
Oh, this R? Oh, that would be like that 0.2. Or sometimes it's like radius of gyration. Maybe it's like something else, like mr squared. Radius of gyration is like a way of finding a number to represent an object, but here we can call it. Yeah.
What happens to the R and AX over R?
The AX over R?
If you replace a double out with AX over R, in like the second line down.
Oh, we had like R squared and AX over R, so we ended up with just MR AX.
Oh, that's R squared.
Yeah, because like in general, moment of inertia is some kind of like mass times R squared, or maybe it's like A squared plus B squared, but some kind of value of like distance squared. Kilogram meter squared is your moment of inertia. Yeah, so A, in this case, if you pull on it forward, it goes forward. Yeah.
Doesn't it depend on the tension though? 'Cause if you had it at less than 5 newtons, you would have got a negative number, right? Because you would have had 0.2 times 5.
0.2 times
Or if
5.
you at 4 newtons, you would have had 0.2 times 4. So you would have had 1 minus 0.8. So you would have 0.2 and then moved it over negative 0.2.
But I think, like because force of friction is directly proportional to that tension, if I made it 1, all the numbers would just decrease by 10. Like force of friction would also be 10 times. Yeah, yep. Because MAX has to equal tension minus force of friction, and then, yeah, kind of moving that way. Kind of weird, wacky. But yeah, there is a case, if you keep increasing the angle, then things change, because now it's a little different, but because now you're reducing. Anyway, because if you pull it directly up, then the tension's not pulling you forward at all. Now you unspool. MAX is negative. So there's got to be some transition where it doesn't move at all. Nice. Anyway, similar to flywheel, but a little different. All right. Sorry, what else do we have? What else?
We need to give it a mass as well. One.
Yeah, we can call it like 1 kilogram sort of thing. But what else did we have? I saw like some people thinking about like 4-bar linkage. What happens if like L1 and L2 are the same, or sorry, L1 and L3 are the same?
Yeah, the rotation rate equals.
It should be the same, right?
Yeah.
Yeah.
The equation is true that the rotation rate is.
Yeah, you could say, like, all right, create that vector equation, then show that theta 1 dot has to be m.
Windshield wipers are like a 4-bar linkage, but wouldn't dy and dx change in that?
Oh, why would dy dx change for that one?
Like, what's your other fixed point?
In the windshield wiper?
Yeah.
So what happens, like, in your windshield is kind of like like it's connected down to the actual linkage system. And then down here, this is where I have, oh, well, I guess let's extend it. So like in kind of buried into the hood of your car is a small 4-bar linkage with a big long extension off of the rocker arm. So the rocker arm is just doing, going from whatever, 100 degrees down to 0, then back up to 100, and just attach a big long windshield wiper to it.
So is the advantage of that that you have to like, I don't know, I guess rotate it less to rotate it more? That didn't make any sense.
So here, like advantage of having like a 4-bar crank and rocker is that now when I plug in my motor, I can just say like, all right, just go nuts, spin, just keep spinning. And the resulting motion is back and forth, rather than having to design a windshield wiper that spins, or having to design a motor that constantly reverses direction, where you're reversing the polarity of your motor every quarter of a second.
Is it like an energy related advantage to spinning that like smaller one at the bottom?
Oh, do you save energy that way?
I guess not actually.
You don't save energy, but you wear down your parts a lot slower because you're not reversing. I mean, you have like this one reversing direction, but like your windshield wiper does reverse. So that one's just like pretty simple bearings, and those are easy to deal with, rather than a motor that that'll kind of burn out pretty quickly if you're forward, backward. And it's easy enough to just like hook up a 4-bar, do all sorts of stuff with 4-bar linkage. Yeah.
For that one, but the 4-bar we were looking at earlier, L2 was parallel to the graphic.
Yeah, and L2 is always parallel, right? Yeah, because now we're describing like a parallelogram. And these are like, that kind of thing is great for like trying to lift, like if you're trying to lift a person, if you just have like, if I just like take this person and say like, okay, let's lift you up. As I rotate it, now the person's gonna like fall out of the basket. Yeah, so it's fine for catapult, but not ideal for an actual person. So instead, definitely not OSHA approved. Instead, attach 2 bars on there, and that's how like all cherry pickers work, right? Like if you look at them, there's always 2 parallel bars. And now, as you rotate them, these things rotate this way, but this guy follows. Also, he's still moving in an arc.
Wait, shouldn't there be another one?
Oh, you mean over here? Yeah, this one's kind of like fixed to our cherry picker sort of thing. But yeah, now we have like a parallel OSHA approved motion. All right, what else? What else are we thinking about? Yeah.
This is like a stupid question, but I was thinking about it yesterday. You know how like, Looney Tunes, they have like that box where if you hit the button, like the punching glove comes out, and there's like a ton of linkages. So like if you squeeze them, it just shoots out. Is that?
Oh yeah.
Is it the same idea of like linkage? Do you know what I mean?
Yeah.
Punching box.
You can also think of scissor lift.
Yeah.
Scissor lift. Yes.
Yeah.
That's a better idea. Scissor lift. Home Depot.
think that'd be positive. Yeah, it's just like a lot of inches.
Kind of like this.
Yep.
Yeah. Yeah, what's going on with this one?
So you have like,
How do we even create like constraints to get this thing to move? Because we want it to scissor the motion, right?
Aren't they all moving at the same rate? The ones on the other side moving inversely to the other one. Well, all the interior angles are the same.
yes, interior angle theorem.
Okay.
Or something.
Yeah. Interior angle.
But the idea is like,
Well, first off, like, let's say we want this side to move that way.
yeah,
What do I want to do to this side?
anchor it or like squish.
Anchor both?
No, anchor the left side and push from it. You know what I mean? Like have a dude stand there.
So what do
Collapse the two frames towards each other.
So we want to anchor something. What do you want to anchor?
You need something to hold it so like otherwise both sides just go up.
Well, right now, like if all we think about are just the hinges and we're just like throw it, it's not gonna, nothing's gonna create the scissoring motion. So we need something to like say, all right, this piece is not moving. Now do something. What do we want to do? Yeah.
You would think, like you fix one, like in that, so you fix the bottom one and then have a force down on the top like that.
So say like one of them, and again, like think about like if it's a Looney Tunes box, at the bottom of the box, what's the, yeah, because we have like a big comically large kind of punching glove, right? Yeah.
So yeah, you need to anchor it.
So anchor one. What do we do with the other one?
Bugs would just apply a downward force on that upper left one.
Down force?
Downward or upward.
Can it move?
Well, we wanted to punch Wile E. Coyote, so it's gonna go down.
Oh, are we out of time? Sorry, I get too excited with All right, so main thing is like this one.
You push it straight down, right? You have to. Yeah.
Yeah, like that.
Wait, why'd you?
This one's got to like slide, right? Like, because we don't want it to move forward.
Oh, so this is a prismatic situation.
Make a prismatic constraint of that thing so it doesn't move forward. What do we think about like if I was going to do this, I would just start with like just these parts. And for the most part, we built a slider crank with extra stuff attached to it, right? Because we needed a fixed part and a sliding part. What do you think about this? Like creating like vectors on that one? Because what you do is start O, A, and B, create vectors between those, and then there's going to be a mirror image of those on the other side. Vector constraints that way. All right, we could try it. Maybe something like that. All right, maybe, yes, no, no.
That is a 3-bar lead. What are you talking about?
All right, try it. Yes. All right, sounds good.
Mike, you know what? I thought I was a T-ball player. Good job, T-ball. Wait, so you write it down. And then it's just. So you have one. So you have what? Still one. You have 1 degree of freedom. Oh, I guess you do.
Yeah, just 1 degree of freedom.
So you would solve that the same way we would solve the 4-bar linkage, right? Can you use the same system or just come up with a new one?
It would be. It is a different. Like it's a different set of constraint equations. So really, what you care about is kind of like as that thing pushes down, how fast are the other pieces going out?
So I guess we consider that as you push that down, that angle in between is gonna decrease.
Yeah, that one decreases and makes the triangle sharper, like more acute, and pushes forward.
I guess I understand. We always go to a bunch of people saying they had internships, and I asked them, they're like, yeah, we don't hire anyone. That's great.
Yeah, that's like.
Yeah, that's it. I was like, I'm really interested in that round, and they're like, well, yeah, okay.
Yeah, I wasn't.